Okay, we are learning about sampling of a signal. Okay, so if we simply speak, the sampling is the process of converting a continuous time signal, continuous time signal into a discrete time signal. Discrete time signal. So that is the sampling, converting a continuous time signal into discrete time signal. Okay. So in this course, we mainly focus only on sinusoidal wave, sinusoidal signal. Okay. So we mainly focus on continuous time sinusoidal signals and discrete time sinusoidal signal. So we choose sinusoidal signal for our simplicity, but these theories and the knowledge you can apply to solve or analyze more complex signals. Okay. So in last tutorial, uh, you have learned some properties of continuous time sinusoidal signal and discrete time sinusoidal signal, no, with Dr. Udesh. Okay, so the first one is we can represent sinusoidal signal as like this. Cos 2, 5, I will put capital T here, capital F here, capital F by theta. So this is radian. This theta is the phase shift and it is measured in radian. Okay, so this is the continuous time sinusoidal signal in time domain. Okay, this is the time domain representation of a continuous time signal. Okay, and if we write the discrete version, it will look like this. Xn is equal to A cos 2, 5. I will put here simple f. Okay, Fn plus theta. Okay, so why I put here, why I just put this as simple f, because this f and this f is not equal. Okay, we call this as the nominal frequency. Okay, so let's see what is that mean in future. Okay, so anyway, this is the continuous discrete time sinusoidal signal representation. Okay, and this n is an integer value that will lie between minus infinity to plus infinity. Okay, that means -1, 0, 1, 2, like so on up to plus infinity. Okay, so this the n is an integer value, plus or minus integer value. Okay, and okay, if we draw this signal, if I draw the continuous time signal, you already know that. Okay, actually all these continuous time sinusoidal signal property we have learned. Okay, but we didn't learn about the time discrete time sinusoidal signal. Okay, but in continuous time case we know these things. Okay, so we can draw the continuous time signal like this. Okay, so there is a phase shift here and it will go like this. Okay, sine signal, and this is t, normally measured in second. Okay, and this is the xt. Okay, level, and this will be plus a and this will be minus a. So this is the continuous time signal. So if we draw the discrete time signal, okay, if we draw the discrete time signal, so it is n. Okay, and here it is xn. Okay, so this is discrete version of the signal. Okay, so in we know that n can be minus infinity to plus infinity, so there can be -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so on. Okay, so this n is an integer value. It can be plus or minus. So here we draw the signal in only in plus side. Okay, so we will draw it in plus side. Okay, so so here we can draw this line like this here. Okay, and this here it will look like this, and here it will look like this, and here it will look like this, here like this, and here like this, here like this, here like this, here like this. Okay, so we will get this kind of signal, no? Okay, so this kind of signal we will get if we draw the discrete version. We have only just some value. Okay, so if this this is a voltage signal. Okay, voltage signal, this A and minus A will be voltage values, no, voltage levels. Okay, and if this is the discrete version of this signal, voltage signal, so these are some voltage value. Okay, these are some voltage value. If it is a voltage signal, for example, okay, this will be some voltage value like this. Okay, so this is the value corresponding to 0, and this is the voltage value corresponding to 1. This is the voltage value corresponding to 2. This is the voltage value corresponding to 3. This is the voltage value corresponding to 4. This is for 5. This is for 6. This is for 7. This is for 8. This is 9. This is for 10. And this is for 11. Okay, so like this. So we will get the discrete version like this. Okay, so so this t is measured in second, no? So how this n measured? Is it second? Okay. So if we select n as -2, -1, 0, 1, 2, 3, 4, 5, 6, is it second? 0 second, 1 second, 2 second, 3 second, so on. Or millisecond, 0 millisecond, 1 millisecond, 2 millisecond, 3 millisecond, so on. is it? So how can we define this n? Okay, so we know that this is discrete time signal. This is discrete time signal. So it is time. It is the time domain signal, no? Okay, so here this time is a continuous variable. Continuous variable. Okay, this time is a constant variable, and this n will also should be a time value, some time points. So corresponding to this 1, 2, 3, 4, 5, 6, definitely there should be a time value, no? Okay, so this there should be a time, the corresponding time point, time value here. Okay, so then how can we map this n with time? How can we map this n with time? Sorry. So that is the problem. Sometime you may think. Okay, so how can we map this n with t? Okay, so so in later you will get the better understanding of this thing. Okay, but up to this time try to get this idea. Okay, so this is the continuous time signal. Sorry, this is the time discrete time signal, and this is the continuous time signal. Okay, so if we take this discrete time signal means, okay, we can define it as, okay, we can define it as sampled version of this time domain signal, this time domain signal, xt, sample version of xt. So we can view or we can interpret this discrete time signal as a sampled version of xt. Okay. So these are we call sample. Okay, these are we call sample. Okay, and this n we call the sample number. Okay, so this n is a sample. It is okay. It is not directly time. It is sample, number of sample. But we should have a way to map this sample with time anyway. Okay, so we will see it. Okay, so this n is a sample, number of sample. That is why we take it integer value here. -2, -1, 0, 1, 2, 3, 4, 5, 6. Other than we get the rational value. Okay, decimal value 1.2, 1.3, like that. Okay, we will. That is why we take this n as 1, 2, 3, 4 integer value, because this n represent the sample, number of sample. Okay, so these are the sample. Okay, so if this is the voltage value, if this is the voltage signal, so we get some sample. Okay, we get some sample of this signal. With some time we get some sample like this. We get here a sample, we get here another sample, we get here another sample, like this. Okay, so we get some sample. Okay, corresponding, and the corresponding sample is named as 0, 1, 2, 3, 4, 5, like that. Okay, so okay, so what is our problem? Our problem is that how we map this in with time. Okay, so definitely there should be a time value, no? Okay. So actually, if you get these two sample, 0 and 2 nearby sample, there is a time gap. Okay, so between these two sample, there should be a time gap. Okay, so with this sample and this sample, this time gap is there. Let's say TS1. Okay, so this time gap is TS1. Okay, and between this first sample and second sample, there should be again a time gap. Let's say TS2. So this time gap is TS2. Okay, and also here between this sample also there is a time gap, TS3, and here TS4, TS5, like that. Okay, so there are time gap actually between these two samples. There is a time gap. Okay, so here we can take this time gap. Okay, this is the between first two sample and second two sample, TS2, the next sample TS3, TS4, so on. Okay, so you can select different time gap. Okay, that means this time gap may be different from this time gap. This time gap is different from this time gap. Okay, for example, if TS1 is 1 millisecond, okay, so TS2 can be 1 microsecond. This can be 1.2 nanosecond. This can be 1.0.003 second, like this. Okay. So we can define this time gap with any value, with any time value. Okay, and also we can define, we can take the constant time gap. Okay, so from this to this, there is some certain time gap, TS, and from here to here, also there is a certain time gap, TS2, TS, the same time gap, and from here to here, the same time gap. Here to here, again, same time gap. That means from this time gap is TS, and this time gap also TS, and this time gap again TS, this time gap again TS, this is TS, this is TS. So we can select constant time gap or uniform time gap. Okay. Okay. So normally we would like to select this constant time gap rather than this different time gap, because this is much simple. No, this is much simpler, and also for analyzing and calculation, purpose, it is the best way. No, it is the simple way. So this is if this way is not good, okay, and it will be more difficult when we are analyzing and calculating different stuff. Okay, so normally we select this time gap as a constant value. Okay, so in future you can see that this time gap we called as sampling time. Okay, sampling time. So that is the time duration. Okay, so that is how this n and time is interrelated. So if you want to find the time point of this third sample, that is 3 by ts. Okay, that is the time value here. And if you want to find the time value here, it is 9 ts. If you want to find the time value here, it is 11 ts. If you want to find the time value of n sample, it is n ts. Okay, so on. So that is how this n and t is interrelated. So this n is number of sample. Okay, so get that idea. Okay, next you have learned about the periodicity of this sinusoidal signal. So you know that all sinusoidal are periodic. So we can write it like this. Okay. So this T is called fundamental period. Fundamental period. Okay. That is the time. That is the time to complete one cycle. Okay. In sinusoidal case. Okay. So if this is from here, that there is one cycle, from here to here, one cycle. Okay. So that time is T. That is the fundamental time. So after this T time, this value will again repeat in here. Okay. So this is the fundamental period. Okay. Normally measured in second. Okay. So this normally measured in second. Okay. So so also we can define some parameters here. Okay. So this is time taken for one cycle. Okay. So if you want to find the number of cycle per 1 second, that is 1 by t, no? This is time for one cycle. Then if you want to find the number of cycle per 1 unit, it will be 1 by t cycle, no? So it is number of cycle. Here it is number of cycle, okay? Number of cycle per 1 second. That is 1 by t. And we call this as a frequency, no? Capital F. Okay. And also you know that this is one cycle, and one cycle have 2-5 radians. Okay. So to complete 2-5 radians, it take capital T time. So if I get the angle per 1 second, that will be I can get it using 2-5 by t. That is the angle per 1 second. No, angle in radians. Okay, this is in radians per 1 second. So that what is that? That is we called omega, the angular frequency or angular velocity. This is angular frequency or angular velocity. Okay, so this is omega. Okay, so I think already you know the units of this stuff. Okay, so this t normally measured in second. So this f is 1 by t, 1 by second, that means per second. This is per second, that means it is hertz. Okay, so this hertz unit is hertz, and this unit is second. Okay, so the angular velocity omega, the unit is radian per second. Okay, so if I summarize all these three together, we have 25t is equal to omega, and it is equal to 25f. Okay, so this omega is in radian per second. This is per second, that means hertz, and this is second. Okay, so these are the unit. Okay, so we have know this. Okay, we know this already know. Okay, so let's see in case of time domain, sorry, discrete time version. Okay, so discrete time signal. Okay, discrete time signal. So here you can see that. Okay, we have some sample here. From here to here we have some sample. Okay, so if I draw this signal, it will look like this. No, it will look like this. Okay, it is also a sinusoidal pattern should be there like this. Okay, okay. So here we only consider the sample, not time. Sample. Okay, number of sample. So what is the condition for the periodicity of this discrete time signal? That means after some number of sample, we should have the same sample. For example, say this is, and this sample is same. Okay, this sample is repeated here. Okay, so if we count the number of sample, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have 9 sample there. Okay, so after 9 sample, we get the same sample here. Okay, so here we, in discrete time domain, we measure that as a number of sample, not with the time. Of course, here also a time duration, okay, and time duration is exactly equal to this t. Okay, so this is a one cycle. From here to here, it is one cycle. Okay, but we do not take time into account. We only consider the number of samples. Okay, so to be periodic of discrete time signal, the condition is xn plus capital N should be xn. So this n is a number of samples. Okay, so this n is a number of samples. So here, for example, we take n is equal to 9. Okay, we take n is equal to 9. That means after 9 sample, 1, 2, 3, 4, 5, 6, 7, 8, 9 sample, we will get the same sample here. Okay, so n is equal to 9 here. I take it as an example. Okay, so, and also we can get this relationship for the time discrete time sequences, also discrete time signals. Okay, so so this is number of sample. So what is this then? Number of sample, it is number of sample per one cycle, no? Am I correct? It is a number of sample per one cycle. Here, if this is a sinusoidal signal, so from here to here, it is one cycle. From here to here, it is one cycle. From here to here, it is one cycle. Here to here, it is one cycle. Okay, so here I get 9 sample. Here I get 9 sample per one cycle. 9 sample per one cycle. Okay. So what is this? N is the number of sample per one cycle. Okay. So N represent one cycle. So if you want to find how many cycle per one sample, so you need to find how many cycle per one sample. So how you find? Here n within n sample, one cycle is there. Then in one sample, okay, 1 by n cycle should be there. Okay, so this is the frequency of the discrete time signal. Okay, so here 1 by n is equal to capital F. Okay, so in case of continuous signal, 1 by t, okay, 1 by t is equal to capital F, and it is hertz per second. Okay, but here it is per sample. F is defined cycle per sample. Here F is defined as cycle per time, cycle per second. But here the F is defined as cycle per one sample. Okay, so this is one fact. Okay, the other thing is, so n represent one cycle, no? So 2 5, one cycle has 2 5 radians. So if you want to find the angular velocity, angular frequency, so you have to find 2 5 by n. Okay, so here it is 2 5 by t, but here in discrete time it is 2 5 by n. You will get omega. Okay, and of course you can see that 1 by n is equal to f, so also this is equal to 2 5 f. Okay, like this. Okay, so same thing is here, but the unit is different. Okay, so what is the unit of this? It is radian per sample. It is radian per sample. Here it is radian per second, but here it is radian per sample. Sorry, this is simple omega, radian per sample, and this is per second, that is hertz, but here it is cycle per sample, that is also in hertz. Okay, normally we put it in hertz. Okay, because sample also we can convert to the time. Okay, so normally we represent it in hertz, but it is actually cycle per sample. Here cycle per second, here, but here it is cycle per sample. Okay, so and this n is number of sample. Okay, so this is sample, but this t is in second. Okay, so uh, this is the property we have learned next. Okay, and after that we have learned very important property that is unique to the discrete time signal. It is not in continuous time signal. So what is that? That is, if we consider this kind of signal, omega naught n plus theta. Okay, so of course this can be omega naught can be replaced by 2 5 f naught. Okay, but here we only consider the omega naught, not 2 5 f naught. You can replace the 2 5 f naught here, no problem, because omega naught n is equal to cos omega naught plus 2 5 k n plus theta. Okay, and this k is also an integer value. Okay, integer value. Okay, And okay, this n is all, the k is also integer value. Okay, so what you can see here, you can see here, so this signal cos omega naught n plus t signal can be equal to many other high frequency signal, no? Okay, can be mapped to other high frequency signal. So this discrete time signal, you will same discrete time signal you will get with more frequency, with higher frequency. Okay, or lower frequency, minus frequency. Okay, the both can be there. Okay, minus or plus higher frequency. If we tell like that, I think it is fair. Okay, so you can see that here, due to this property, you can map many high frequency signal. Okay, many high frequency signal. Okay, many high frequency signal into one low frequency signal. Okay, you can map very many high frequency signal into one low frequency signal. Okay, so that is the idea here. Okay, so this condition, you can see that this condition satisfy when this n is integer. If this n is an integer value, that is 0 to 1 or minus plus or minus 1, plus or minus 2, so on, plus or minus infinity. So if this signal is plus or minus 1, plus or minus 2, plus or minus infinity, so you will get this identity. You will get this condition, otherwise it is not same. Okay, so so this is satisfied when this n is equal to integer value, and it is only in discrete case. Okay, not in continuous case. Okay, so another thing we have learned that this omega can be very high frequency, can be a very high minus frequency, or normal minus frequency, or can be zero, can be very low plus frequency, can be medium frequency, can be very high frequency. Okay, so that omega will lie between minus infinity and plus infinity. Okay, so if you get a low frequency, that signal will look like this. If you get more high frequency, that signal will look like this. Okay, and if you get another very high frequency, that signal also will look like this. Okay, and if you get another frequency, high frequency, it will look like this. Okay, and if you connect another very low frequency, it will look like this. Okay, so what I want to tell you is that different frequency value will generate different waveform pattern. Okay, different frequency, different value of this frequency omega, different value of omega will generate different value of signal. That is why it is we get it from minus infinity to plus infinity, very high frequency to very low frequency we can consider, including zero. Okay, so in same manner, f can be calculated as minus infinity to plus infinity, because f is equal to, because omega is equal to 2 pi f. So in this case, it is so on like this. But due to this condition, in case of discrete time signal, you can see that, okay, you can see that many higher frequency, okay, many higher frequency and some frequency can be mapped. Okay, actually infinite number of frequency can be mapped to one frequency. Okay, this case can be 0, 1, 2, 3, 4, 100,000, 10,000. Okay, 1 lakhs, 2 lakhs. Okay, like this. 10 million, 30 million, like that can this k can value. That means all these high frequency and low frequency map to this omega n naught. Okay, so you will generate the same pattern. Here you will generate different pattern. If you get different frequency, you will get different pattern. But here different frequency you can map to one pattern. So at all these instant, the one pattern you will get. Okay, so here the omega only lie between -5 and +5. That means any value, any omega value we can map. Okay, for any omega value, this omega also we can get from -infinity to +infinity, no problem. But okay, this omega value also we can get to -infinity to +infinity, no problem. But all these value will map to -5 and +5 range frequency. Frequency within this range, all this frequency will be mapped. Okay, so here omega is from -infinity to +infinity. Okay, we will see this in Matlab. Okay, so here the f is from half to -half. Okay, so this you can get from omega is equal to 5f. Okay, I don't it, so you can calculate this. So this is another condition for discrete time signal. Okay, and this is very important parameters you have to keep remember. Okay, in case of continuous signal, this omega and f can be different value and it will generate different waveform. But in case of discrete time signal, many higher and lower frequency signal can be mapped to one specified signal called omega naught. Okay, so we will take a Matlab example to get the idea more clearly. So here I will choose omega naught as 5/2. Okay, omega naught as 5/2. Okay, and I will get k is equal to 1. Okay, so I have signal cos omega naught n, and I have signal cos omega kn. Okay, so here omega naught is 5/2. So omega k will be 5/2 plus 25k. That means 5/2. Okay. So we will see a Matlab program to get this idea clearly. So this has proved in previous session, but here we are going to see it. Okay. So I define this function as x1 and this high frequency watch function as x2. Okay. So I will go to the Matlab program. Okay, so this is our program. So I have modified it so that you can put any value here. Okay, so I will put k is equal to 1 and y is equal to 5/3. Okay, I will put it to 5/3. Okay, so here so omega naught will be 5/3. Okay, 5/3. So if I plot the, so first let me plot the continuous waveform. So I can use plot command, plot n x1. Okay, I will put the color here. I will put red here because in discrete also I put the red color for low frequency signal, and I put plot then x2, and I put blue here. Okay, that is not the issue. Okay. Okay, so I'm going to plot the continuous time signal. So we have to we have to get very nearby values for this n. Okay, so I will get 0.01 increment. Okay, 0.01 increment. Okay, then if I plot this, some error message is there, plot text and I can double. Input line 11. Okay, sorry, this P. And if I write there, I get only one. What is the problem there? Put hold on here. In the same graph, when we plot it, we have to insert this command. Hold on. Okay. So now I think it is okay. So you can see that we have two signal. This is the red one is the low frequency and blue one is the high frequency signal. So we get omega naught as 5/3 and omega k will be 5/3. Okay, so within one circle there should be 5 circle. Okay, so within one circle of this low frequency signal, that is this one. Okay, and it is here to here one circle. Okay, here to here I will put 0 here, then it will be somewhat clear. I will put it 0 to 8. Okay, so you can see that what happened. Okay, so so here 5/3 and I wrote it. Okay, so here we have put the phase shift now. Yeah, I have put the phase shift. I will remove the phase shift also. Okay, this phase shift is not affected to the waveform, but for the first time I will remove that phase shift. Okay, okay, okay. So you can see that from here to here it is one circle. From here to here it is one circle. So within that circle there should be 5 circle of the blue curve. No, so this is one circle. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. So one circle there, no, 7 times 5, 2, 2, 5. Yeah, sorry. The omega k will be 7 5/3, no? 5/3 plus 2 5/3. Sorry, 5/3 plus 2 5. Okay, that means 7 5/3. So 7 times greater than the low frequency low frequency signal. Okay, so here it will get 7 cycle. No, 1, 2, 3, 4, 5, 6, 7 cycles there. Okay, so this is the so what you here what you should note down here is we get two waveform. No, we will not get the same waveform, we will get two waveform. Okay, so one is the low frequency signal, another is a high frequency signal. Okay, that is the first thing you have to understand. Okay, So, but you can note down one special property here. Okay, what is that? Okay, so if you get this n, this is the line, no, in axis. So it is from 0 to 8. Okay, if you get 0, 0 0.01, 0 0.02, likewise decimal value also, you will get two waveform. Okay, if you draw the discrete version, also you will get two waveform. Okay, I will show it. I will comment this, and this will be uncomment. Okay, so I will put it in one. So if I run this, okay, so you can see that. So I will because here I have get 0.001 increment, so it will look like a continuous value. So I will choose 0.1 increment, so you can see the discrete type signal very clear. Okay, so you can see now, no? So you can see that you have two signal, no? This red one is a low frequency signal and this blue one is a high frequency signal. Okay, so that is happened because we take decimal value of this n. So if we take only one, so let me show you. If I comment here, okay, and if I uncomment, okay. So when I draw the, I'm going to plot the continuous signal. So you can see that, see, when this n is integer value 0 to 8, so note down this blue and red curve is at in one place, no? So you will get 1 here, and at 1 this blue and red curve will be the two signal is crossing each other. Okay, so that means this level are also same for both signal. Okay, and if you get this 2, this point also same for both signal, and 3 same level, and 4 you will see same level, 5 same level, 6 same level, 8 same level. Okay, so if you get n as an integer value 0, 1, 2, 3, as well as -1, -2, -3, so on, you will get same sample. Okay, for both blue and red curve. Okay, so let me check if we get the same sample. Okay, so I will plot it in two plot, otherwise you can't see the two signal because one signal is exactly upon another signal, so you can't see one signal there. Only see one signal, you can see only one signal because other signal is under the another signal. Okay, so you can't see it. So I will plot it into different plot. Okay, so you can see that we have exactly same signal, no? Okay, so if you consider this x1 and x2 value, these are same value you will get, no? Okay, so you will, for both case you will get the same signal. Okay, so you can put this k is equal to 2, 3, 4, 5, 6, any value. Okay, any big value, but you will get the same result. Okay, here you can see the same same value is there and same graph is there, no? Okay, so you can see that many if you get 1,000 or something, okay, again you will get the same value. no, the value is not changing, this x1 and x2, so you will get the same value. Okay, so you can see that there are infinite number of signal. Okay, for infinite number of this omega k value, okay, you will get the same pattern. Okay, so if I put here, you can remember that when we put the 5/2, we will see a small difference. Okay, but it is actually negligible. Okay, so you can see there is the difference between 2 points, but this difference is very small. Okay, because this happened because of the calculation of the point. Okay, so if the Matlab is say calculating some number, say 10/3, that is 0.3333, so on. Okay, so Matlab has to approximate it so to some decimal value, to some decimal number. So when he approximate it to one decimal number, so this value can be slightly changed. Okay, that is the because of the practical calculation, but theoretically it is not happen. You will get the same value. Okay, so understand it, because this different value, very small different value. Okay, this value difference is very few decimal value. Okay, it happened due to the approximation. When we are calculating, we have to approximate the number to some specific length. Okay, so when we approximately, we will not get the exactly same number. Okay, when we approximate in the decimal value, we will not get the exact number. Okay, but it is very near number. Okay, it is a very near number. Okay, so this program is correctly working, and also this theory is correct. This theory is true. Okay, only this thing happened because of the calculation limitation. Okay, the decimal value calculation limitation. I hope you get that point. Okay, so you can try this with different omega naught. Okay, with different omega naught and with different k. Okay, different k, and of course you can introduce some phase shift here. Okay, no issue, but you have to introduce the same phase shift for both signal, then you will get the same answer. Okay, so this one and this one is nearly okay, no? Okay, nearly okay, exactly match. Okay, so you will get the plot, same plot you will get for both signal. Okay, so try to get this antenna, try to get that idea. Okay, so many signal can be mapped to one specific signal because of this property of a discrete time signal. Okay, so I think now we can start the sampling. Okay, so we will see the sampling. Okay.